In the previous episode, we explored linear regression and extended it to polynomial regression by explicitly creating higher-order versions of the input variable. That method allowed us to model nonlinear relationships by manually transforming the data. In this episode, we will see how support vector machines, or SVMs, can achieve similar nonlinear transformations implicitly without us having to create polynomial features by hand. To begin, we import our dataset using pandas and preview the first few rows, just as we've done throughout this series. The dataset again consists of vehicle speeds and their corresponding stopping distances. Next, we import the SVR model from scikit-learn. The SVR model allows us to specify a kernel, which determines the kind of transformation applied to the input space. For this example, we focus on the polynomial kernel. When choosing a polynomial kernel, we must also specify the degree of the polynomial. So we set the degree to 2. After configuring the model, we fit it on our training data. Once the model is trained, we generate 50 evenly spaced speeds between 0 and 60 miles per hour using NumPy's linspace. We reshape these speeds into a column vector, feed them into the fitted SVR model, and obtain predicted stopping distances for each generated speed. We then plot the predicted curve together with the actual data points. The visual result shows a smooth quadratic curve that matches exactly what we saw in the previous episode using explicit polynomial regression. This confirms that SVR with a polynomial kernel of degree 2 is performing the same transformation, but implicitly and automatically. The important idea here is that nonlinear transformations are not limited to polynomial regression. SVR supports a variety of kernels straight out of the box. These include the linear kernel, which corresponds to ordinary linear regression, and 2 other kernels called sigmoid and RBF, radial basis function. The sigmoid and RBF kernels are extremely popular for classification tasks, and we'll explore them more deeply in future videos. To better understand the behavior of all 4 kernels on this dataset, let's generate a comparison plot. First, we create an empty matrix with 50 rows and 4 columns to store the predicted values for each of the 4 kernels. We then loop over the list of kernels: linear, poly, sigmoid, and RBF. For each kernel, we train a new SVR model on the same training data and then store its predictions in the corresponding column of our matrix. After computing all predictions, we plot the curves for each kernel together with the original dataset. The results show that the linear and polynomial kernels perform reasonably well, with the polynomial kernel fitting the data most closely. However, sigmoid and RBF produce curves that clearly do not capture the trend in this dataset. This is expected, since these kernels are not particularly suited for this specific regression problem. They rely on different kinds of nonlinear transformations that tend to perform better on classification tasks rather than noisy, one-dimensional regression. With this, you now have a solid understanding of supervised regression models. Throughout this series, we have explored k-nearest neighbors, decision trees, linear regression, polynomial regression, and now support vector regression with multiple kernels. Each of these methods approaches the regression problem differently, and together they represent a strong foundation for understanding modern machine learning. For everyone who has followed the entire regression series from start to finish, I truly appreciate your dedication and effort. In the next episode, we move on to supervised classification models, where we will see how these algorithms decide between categories rather than predicting continuous values. I look forward to seeing you again in the next video.